Okay, today we are going to start the linear kinetics. Okay, so actually we are done with the linear angular kinematics for the second exam. That's why it's time to start the linear kinetics. Linear kinetics means linear motion plus kinetics. And as you learn, and as you may remember, kinetics means the study of explanation of motion, which means all these quantities in this chapter will be used to explain linear motion. Okay, so we are going to start the concept of Newton's laws of motion. Okay, so there are three laws of motion discovered by Isaac Newton. First law is law of inertia. Law of inertia means the body remains at current state of motion unless acted upon by external forces. Okay, so I'm highlighting this one in red. State of motion means velocity. Which means body remains at current velocity unless we are receiving external force from outside. And then there are two different types of inertia here. Okay, static inertia and dynamic inertia. Static inertia means if something is not moving, the object has a tendency to keep stationary. It wants to stay there. So on the other hand, dynamic inertia, which means if something is moving, it has a tendency to keep moving. Okay? For example, here there are two figures here. Okay? Actually, yellow wheel means this is moving, and then this empty circle means this is not moving. Okay? Here, actually, this was not moving, right? Static inertia. But what if these cards suddenly move this way? If then the box on top of this card will fall like that, because this box has a steady inertia, which means since this was not moving, this one has a tendency to be stationary. Okay, this steady inertia. How about this one, dynamic inertia? Still inertia, right? But with dynamic inertia. Okay, look at this. Okay, this system is moving. Okay, together. Okay, wheel, cart, and this is the box on top of this cart. And then they are moving together. And then what if this car suddenly stop? Then what's going to happen to this box? This box will fall this way. Because this one has a tendency to keep moving, dynamic inertia. So we can have two different inertia here, steady inertia and dynamic inertia. And I would like to talk more about inertia to better understand the laws of motion, which is first law of motion, the law of inertia actually. And the inertia is the tendency of an object to keep the current state of motion, as I mentioned, to keep current state of motion, which means to keep current velocity. If something is not moving, it wants to just stay there. Whereas if something is moving, the object keeps moving. Okay, that's inertia. And it is also defined as difficulty in changing state of motion. Okay, they keep the same meaning. And then inertia is proportional to the mass of the object. In other words, in linear motion, mass is the measure of inertia. Okay? As I mentioned again, I'm highlighting this one. In linear motion, so mass itself is a measure of inertia. As you can see here. So that the more mass is, okay, it's bigger than this, right? So I can say more mass. The more mass is, the harder it is to stop or initiate the linear motion. Because the measure of inertia in linear motion is proportional to the mass of the object. Okay? And then second law of motion is the law of acceleration. Okay? First law of motion was law of inertia. Second law of motion is law of acceleration. Okay? So force applied to a body causes acceleration. Force causes acceleration. F is equal to ma. It is a law of acceleration. Or if you simply divide all this by m, okay, you will be turning into this simple equation. And then direction of acceleration is equal to direction of the force. Okay. Let me give you an example. You have water bottle here. Okay. So let me apply certain amount of force to this water bottle. Okay. Okay, it moved due to the force applied. Right? So when this one move, okay, this movement is supposed to have what? Acceleration. So my force was larger than friction. That's why I was able to move this water bottle. Okay. Again, when this bottle moves, it's supposed to have acceleration, some amount of acceleration, because force causes acceleration. Okay. And then you just learn law, first law and second law of inertia, law of acceleration. Although these two are the separate concepts, different concepts, those two are very close to each other. Okay, for example, this is from actually the second law of motion, law of acceleration. Okay, so here, okay, this is from law of acceleration. Okay, right here. Okay, under this condition, if f is equal to 0, which means this is 0. In order for this one to be 0, okay, acceleration must be 0. Okay, so if this is 0, okay, 0 acceleration means as you learn constant velocity, constant velocity. So as you learn acceleration, right? So final velocity minus initial velocity in time elapsed. So if this is 0, which means these two are the same, constant velocity. So constant velocity means no change in current state of motion. Okay, current state of motion means okay, dimension of velocity. This is equal to the law of inertia. We can relate the first law to the second law. Those two are different concepts. And then the third law of motion is law of reaction. Law of reaction. Okay, this is for every action, every force, there's equal and opposite reaction. Here, equal reaction means the same magnitude, and opposite reaction means the opposite direction. Okay, opposite direction. So then let me give you the example of this law of reaction. There are two hockey players here. Okay, they just collide with each other, and this guy is moving this way. This guy moving from the opposite direction. And then F1 is force coming from this guy. F2 force coming from this guy. Okay. And when they collide with each other, okay, in terms of the magnitude of force coming from these two guys, F1 and F2, okay, must be equal to each other. Okay. Here equal means the same magnitude, but this one is minus. Okay, which means if we designate the direction this way as positive, the other way must be negative. The reason why he got the negative F2 means he was moving the negative direction, which is this way. Okay, that's why same magnitude but opposite direction, the law of reaction. And then these are examples of law of reaction. The fist fighting. Okay, when for example somebody fight each other, right, like this. Okay, and then when they hit their face using their one fist, right, like this, right, this fist is actually generating or applying certain amount of force to the opponent face. At the same time, although this guy feels very painful, and this guy's face will generate the same amount of force to this fist, but in an opposite direction. Okay, and then propulsion in swimming as well is an example of law of reaction. So he's swimming, right? He's swimming. Okay, so in order to move forward while swimming, okay, push back, right? Push back. Okay, if you push back, right? This red arrow means is pushing the back. Okay, coming from this huge force. If then he's gonna get reaction coming from the water. Okay, he's coming from the water. He's a blue area here. That's why we'll be able to move forward. Okay, while we are swimming. Okay, force and reaction coming from the water to his hand. At the same time, okay, let me give you if I hit the table like this, okay, I just apply certain amount of force to this table. If then my hands is also supposed to get certain amount of force coming from the table to my hand. Okay, the law of reaction. Just the example of law of reaction. And then here one simple example for the law of reaction. Okay, so again there are two acting players here. Okay, and then player number 1 and player number 2. His body mass is 90 kilogram. His volume 80 kilogram. Okay, and F1, again, force coming from this hockey player, 450 Newton. If then how much force is coming from this second hockey player? Okay. The answer is 4, how much? 450 Newton, but negative. Because he is generating force in an opposite direction. Although you got this mass information here, we don't have to worry about this one because this question is not asking us to calculate anything related to acceleration, but it's just asking us to calculate the amount of force is coming from the second hockey player. That's why forget about this for this one. This is trick you guys. Okay, just focus on these two. Okay, according to the law of reaction, this guy is supposed to generate same amount of magnitude but opposite direction. Okay. And then ground reaction force. Okay, this is another example of law of reaction. Okay, this is a very, very important force. Okay, so these are reactions applied by the ground. Okay, which means as long as we have a contact with the ground, like standing, walking, or jumping, landing, okay, we are supposed to get it's called ground reaction force. As I mentioned earlier, it's a very important force for human motion. It can be used as resistance, sometimes also proportion. Okay. So let me just visualize ground reaction. He's running here, right? Running here, and then he just step on this ground. Okay. If then he's gonna let me just draw. Okay. Ground here. Okay, he's running. Okay. When you run this way, okay, he is gonna generate certain amount of force to the ground. Okay, to the ground. Okay, like this. But at the same time, he is supposed to get a reaction coming from the ground to his foot. Okay, so that is a force coming from his contact, but at the same time, he will be receiving the same amount of force coming from the ground to his foot. Okay, so that I can say this is a reaction. As you can see here, reaction. R means reaction. It's coming from the ground to his body or to his foot. And it is a force, right? Force. And then as you learn, according to the vector resolution, this force can be broken down into two perpendicular components. This one and then this one. In other words, here, this and this. FH means horizontal component, Fy vertical component. We can break this force vector down into these two perpendicular components according to vector resolution. So tip to tail, you will end up having this resultant work ground reaction force. Okay, we get this ground reaction force. Okay, another example of law of reaction. Then here, again, this example of law of reaction as well. Okay, so let me use a high jumper example. Okay, so this one should be in the exam, so you should be clearly understand what's going on in this figure. This is high jumping, right? High jumping. Step, take off, and then jump over the bar, right? High jumping. And then he's approaching right here. And let's imagine that we have a bar here, Okay, bar, and the mat here. And then it's a kind of sequence of his movement. I would like to highlight only two instances. Here, and then here. Okay, this is I can say contact. So contact here, and then take off. Okay, contact instant and take off instant. So I should focus on these two. Okay, and then there are a couple of arrows here. Okay, red arrows here and pink arrows, and blue arrows here too. Okay, now let's take a look at these horizontal arrows. Okay, red arrows. Okay, so these arrow means his horizontal velocity. Okay, and then pink arrow means his vertical velocity. But let's take a look at this one. Okay, at this instant, his horizontal velocity was this long. The length of this arrow means the magnitude of this velocity. And then by the time he reaches here, it gets shorter. which means is he slowing down or he is speeding up? Okay, he was slowing down. Okay, when he moved from here to here, he slowed down. He slowed down. And then vertical velocity right here, right? So when he was at this contact instant, okay, it's acting downward, right? He was moving like down like this. Okay, that's why it's acting downward. Okay, and takeoff, but the takeoff, okay, direction has been changed to upward, and then it's acting up, right? Which means at this instant, moving kind of downward, and the takeoff, he just kind of change direction from down to up. That's why he got the positive upward, the vertical velocity. So the horizontal velocity and the vertical velocity for red and the pink arrow respectively. And then more arrows here around the foot, this area here. First of all, I'd like to introduce this one. Okay, he's acting coming from his body to the ground, right? Which means this is force coming from him to the ground. But at the same time, if you have a contact with the ground, we are supposed to get what? Supposed to get ground reaction force, which is blue here. Blue means ground reaction force. Let's compare these two. Okay, force coming from this guy and the ground reaction force. Okay, in terms of magnitude, which length of these two arrows are the same, right? The same magnitude, but direction-wise, the opposite is acting this way. Okay, and then as I explained in this slide, right, this force can be broken down into these two, horizontal and component, according to vector resolution. The same thing. This force can be broken down into horizontal and vertical component. So tip to tail, actually, you will get the ground reaction force, which is a resultant vector. Okay, the bottom line is this ground reaction force can be broken down into these two perpendicular components. But I want to relate this one to this horizontal and vertical velocity. You can use these ground reaction force components to better understand what's going on actually is horizontal and vertical velocities. For example, he was slowing down, right? Horizontally, okay, as I explained earlier. Okay, slow down. This one is primarily due to what? These forces acting in an opposite way of his movement. He was moving this way, right? But this horizontal force acting in the opposite direction. That's why he had to slow down. And then for the vertical velocity, getting downward, right? But he changed direction from down to up, as I explained earlier. Okay, this one. Okay, so this upward, his vertical velocity is primarily due to this vertical component of ground reaction force. That's why he was able to change direction from down to up, and actually, he's gonna maximize this horizontal velocity to jump over the bar. Okay, again, this is kind of very important. It's a combination of ground reaction force and then the velocity. So we can utilize this ground reaction force component to explain what's going on is horizontal and vertical velocity during the high jumping exam. And one more example of ground reaction force, okay, running. So whenever we again contact with the ground, so we are supposed to have some patterns of ground reaction force. Okay, this is a vertical ground reaction force pattern. And then let's take a look at the solid line force. Okay, this one. Okay. So we got this peak, and then some kind of bell-shaped, smooth curve there, and this point is called impact peak, and this portion is propulsion peak. Okay. The reason why we got this point is whenever we put running. Okay. When you run with a hill. Okay, sorry. So whenever you run, you can have two different heel strike patterns. Somebody can run like this, okay? Heel strike first and push up. Heel strike first, then push up. This is typical running pattern. But some people do forceful strike first, okay? This way, okay? Run like this, okay? The side line is coming from heel strike first running pattern. And dotted line is coming from fourth strike, the running pattern. Okay, but when you run with the heel strike first, we're gonna have impact peak and then propulsion peak. Whereas when we run with the fourth strike first, like this, okay, then no impact. It only has a spiral shape curve, and no impact peak, no impact peak. The reason why we got the impact peak when you run with the heel strike first is, so look at this. When you run with heel strike, okay, we are supposed to get boom, strike, hit the ground, and then propel your body to move forward. So impact peak and then propulsion peak. That's why you're supposed to get high impact peak when you run with the heel strike first. But when you run with the fourth strike force, then we're gonna have some bouncing, okay, effect. That's why we're gonna have no kind of very kind of sharp impact peak when you run with the fourth strike. Okay? Which means even for a given running motion, same velocity from same person. Okay? Depending on how they run, in terms of how they contact with the ground. Heel strike or fourth strike first, okay? Ground reaction force pattern will be different. Even for a given running, the same running. Okay? Same thing for the landing. Okay? Assume that I can jump out of this table. Okay? Jump, and I can have two different landings. Okay? I can jump and land like this with a straight leg. And same jumping, but I can land like this. Okay? Okay? So for a given landing, I jumped out of the same table, but I changed the landing technique. First landing, this one will show you very high peak like this. And when I land, okay, smoothly, it will show, okay, the less the impact peak, okay, or contact force. Okay, again, for a given motion, depending on how I land, okay, this force will be there. Which one is safer? Okay, this is safer than this one. The less force acting on your body compared to when you land with your straight leg. Okay, that's what it is. Same thing for the running. Depending on how you contact with the ground while running, okay, this force pattern will be different. The law of gravitation. Okay, this is not the part of the law of motion, but this is another law of gravitation. Okay, discovered by organizing Newton. Okay, so let me simply read this definition. All bodies are attracted to one another due to their mass. So long as you have two different objects, although you cannot see it, okay, there is a attracting force between these two objects due to their mass. That's the law of gravitation. Okay, and this is a Fg. This means attracting force between two objects. Okay, assume that we have two objects here. So m1 is mass of this object, the m2 mass of this object. G represents separation distance. Attracting force, okay, is equal to G, capital G, the gravitational constant, which is this value. Okay, don't worry about this value. This is constant. Just constant to be used to calculate attracting the force. This constant times these two body mass divided by separation distance squared. When you calculate attracting force between two objects based on law of gravitation, okay, based on this definition, okay, this attracting force is proportional to their body mass. Being proportional to body mass means as body mass increase, okay, this force increase. Whereas as body mass decrease, this force decrease. It's proportional, okay, to each other. How about this? Well, this is denominator, right? Which means this force is inversely proportional to the separation distance. Which means as distance increases, okay, force will decrease, and vice versa. All in all, this attracting force is proportional to their body mass, but inversely proportional to the separation distance. Okay? The body weight is example of law of gravitation. Which means body weight is actually force between two objects. Two objects here means my body and the earth. Between the earth and human body, we have attracting force, which is body weight. So gravity exerts to a body by the earth, which means, as I mentioned earlier, there is attracting force between human body and the earth. Okay. For example, here, assume that this is a human body, your body, and then the earth here. And then small lowercase m is your body mass, and then capital M is the earth of the mass of the earth. And then here lowercase r means this is a separation distance from the ground to your center of mass. Okay. And the capital R means the radius of the earth. Okay. This one must be a lot longer than this one, right? Almost is negligible. Okay. So weight here, weight W means weight, attracting force, G. Okay, G is the distance, gravitational again constant. Okay. And then your body mass, okay, the mass of the earth, okay, over separation distance between your body and then the earth. Okay. So again, as I mentioned, this is combine these two to calculate the exact separation distance from your body to the earth. But as I mentioned earlier, this is too small relative to this one. That's why the wave sign, this is almost is equal to each other. So we can simplify this one just simply using the r. Because again, lowercase r is really too small relative to the radius of the earth. So again, you can get this one, G, two masses and the separation distance, which is equal to mg. M is again your body mass. Again, locus G is 9.81. So this G, capital letter M and R squared, this one is actually locus G. Okay, it's a gravitational acceleration, 9.81 meter per second squared. So we can replace this one with 9.81, which is actually gravitational acceleration. If then weight is equal to mass times gravitational acceleration, and the direction is always downward. So we can stop here, and then we'll start friction in the next the video.